Good evening, my dear students, and welcome to this session. Everybody has got the answers? Oh, Smruti, what have you done, saying? So all have got the answer, all have got the links or not? I believe I'll have to send you the links. यार ये नहीं समझ में आता मुझे. How do I share this Unacademy post? कम्युनिटी पोस्ट कैसे करना शेयर, ये नहीं समझ में आता मुझे. चलो, आप सबको तो समझ में आता है, तो शेयर कर देना सारे के सारे अपने ग्रुप्स में. ये रहा, स्वाति बत्रा मैम ने किया है, ये मेरा है, ये मेरा, ये done. And here you have on our WhatsApp group. ये चल रहा है ना, बड़े आराम से, सही है. जितना भी हमने पिछली क्लास में किया है, आज सुबह वाली क्लास में किया है, उसमें कुछ पूछना है आप में से किसी को भी? एनीबडी हैज टू आस्क एनीथिंग हियर? आपकी डांट सुनी है जॉन विक? मेरी डांट सुनी है या सुननी है? अभी एक स्टूडेंट आए थे मेरे पास, अन अकेडमी के पुराने स्टूडेंट, जिन्होंने मेरे अन अकेडमी के सेशंस देखे हुए थे. ही केम हियर एंड ही वाज टॉकिंग अबाउट कि सर मुझे क्या करना चाहिए, मैं यूट्यूबर हूँ. ही हैज मेड द यूट्यूब वीडियोस, 5 लाख व्यूज ले चुके हैं, 700 से ज्यादा वीडियोस डाल चुके हैं और अपना चैनल डिलीट कर दिया है. पता नहीं कैसे कैसे करते हैं. ऊ सर रिसीव्ड, अभी अभी मिला है तुम्हें सेशन का लिंक. चलो अच्छी बात है. चलिए, नाउ वी आर गोइंग टू टॉक अबाउट द सॉलिड स्टेट. और हमने सॉलिड स्टेट के अंदर क्या क्या कर लिया था और क्या करने वाला. दिस इज द एलिक्सर बैच व्हिच इज गोइंग टू स्टार्ट फ्रॉम 16th of August. And here it is what we have as in-depth analysis of PYQs, revision classes, exam strategies, mental mentee programs, mind maps, botany, chemistry, zoology, 6:30, 7:30, 9 o'clock to 10 o'clock. यानी कि 6:30 पे सेशन स्टार्ट होगा, 10 बजे तक चलेगा. जिसने भी प्लस कोर्सेज ज्वाइन कर लिए हैं, फिर उसके लिए यूट्यूब करना जरूरी नहीं है, क्योंकि यूट्यूब और प्लस के अंदर प्लस इज बेटर देन यूट्यूब. तो जो हम यूट्यूब में कर रहे हैं उससे ज्यादा अच्छा प्लस पे करेंगे. सो दिस इज व्हाट वी हैव एज एलिक्सर बैच. दिस इज मी. एवरीबॉडी नोज मी. एवरीथिंग क्लियर नाउ? सब कुछ साफ है. जॉन विक ने सुननी है तो चलो ठीक है बेटा, कोई बात नहीं, आपको डांट भी मार देंगे, हम जरूर स्टार्ट कर देंगे डांट को. नाउ व्हाट वी वर टॉकिंग अबाउट, वी आर टॉकिंग अबाउट द डिफरेंट अरेंजमेंट्स. हमने अरेंजमेंट्स की बात की थी, हमने ये बात की थी किसका क्या कंट्रीब्यूशन है, क्या हमारे पास लैटिस पैरामीटर्स हैं, व्हाट इज द लैटिस साइट, व्हाट इज द लैटिस पॉइंट, कंट्रीब्यूशन क्या है, कोऑर्डिनेशन क्या है, ये सारी की सारी डेफिनेशंस हमने कर ली हैं. ठीक है. तो in solids the constituent particles are close packed, leaving the minimum vacant space. Now let's consider constituent particle as identical hard sphere and build up the 3-dimensional structure in 3 steps. सबसे पहले हम 1-dimensional structure की बात करेंगे, फिर हम 2-dimensional structure की बात करेंगे और फिर हम 3-dimensional structure की भी बात करेंगे. ओके, क्लियर? अब देखो, जब हम लीनियर अरेंजमेंट की बात करते हैं, लेट्स टॉक अबाउट द लीनियर अरेंजमेंट. लीनियर अरेंजमेंट का मतलब ये है कि हम स्फेयर कैसे अरेंज करेंगे 1 डायमेंशन में. हमारे पास ये एक स्फेयर, अरे यार ये क्या हो गया, हाँ ये रहा, ये हमारे पास एक स्फेयर है. ठीक है. अब यहाँ पे जो मैं कर रहा हूं, इसके अंदर बड़ा अच्छा एडवांटेज ये है कि मैं मेरी गंदी गंदी ड्राइंग को भी ये सही कर देता. तो ये हमने स्फेयर को ऐसे अरेंज कर दिया. ठीक है. फिर हमने एक और स्फेयर को अरेंज कर दिया, ये ऐसे अरेंज हो गया. फिर एक और स्फेयर ले लिया, अरे कहाँ गया, ये रहा, इसको ऐसे अरेंज कर दिया. तो इस तरीके से हमने इन स्फेयर्स को अरेंज कर दिया. नाउ दिस इज द लीनियर अरेंजमेंट. लीनियर अरेंजमेंट का सिर्फ एक ही तरीका है, अरेंज इट इन अ स्ट्रेट लाइन. ओके, एंड दे आर टचिंग ईच अदर. अब सवाल ये आता है कि एक क्वेश्चन अपने स्टूडेंट्स के दिमाग में होता है. आज स्पेशल क्लास है? नहीं है. आज स्पेशल क्लास नहीं है क्योंकि आज हमारा सॉलिड स्टेट खत्म नहीं हो रहा है। कल हमने क्लास लगा दी है सॉलिड स्टेट की भी, केमिकल काइनेटिक्स की, और कल हम सॉलिड स्टेट के क्वेश्चंस रात को 8 बजे करने वाले हैं। तो कल स्पेशल क्लास जरूर लगेगी, आज तो नहीं लगी है। ठीक है? क्या टू? मुन्ना कुमार, टू का क्या मतलब है? चलो, पहले कभी हमारी क्लास में 7 स्टूडेंट्स हुआ करते थे, आज की तारीख में हमारी क्लास में 14 स्टूडेंट्स होते हैं, तो ये तो बहुत बड़ी डेवलपमेंट है। 7 से 14 हो गए हमारी क्लास में बच्चे। चलिए, अब यहां पर जब हम इसकी बात करते हैं तो लीनियर अरेंजमेंट करने का सिर्फ एक तरीका। अब एक सवाल जो स्टूडेंट पूछते हैं वो ये पूछते नहीं है, अभी तक किसी ने नहीं पूछा, ये मेरी खुराफाती दिमाग की देन है, वो ये दैट if we have a sphere is a three-dimensional structure. Sphere has the radius and it's three-dimensional. How can you arrange a three-dimensional particle in one dimension? The answer to that question is extremely simple. And that simple answer is that when we talk about the arrangement of particles, we are actually talking about the arrangement of the lattice points. That is the center of mass of these particles. So this is actually the arrangement of lattice points and not the arrangement of the spheres themselves. So that is how it becomes a linear arrangement. Now, when we talk about the linear arrangement, the lattice parameter, that is the only requirement that we have, is the distance between the lattice points. If we know the distance between the lattice points, then in that case, we can make the entire linear arrangement. So we need only one lattice parameter. And that lattice parameter is the distance between the two lattice points. Yes, Mayuk Sen Gupta, special class is absolutely free. Why don't you just join the Unacademy app, download the Unacademy app, register in it, and register using the code AVLive. You can obviously log in using the app on the PC also, from the browser also. That is not a problem. You can just register your phone number. To join with the Unacademy, you need two things. You need a phone number and you need an email address. I hope that email address is not already registered on Unacademy. Clear? If you have already registered it, then in that case, you simply have to log in. Ananya, what did you not understand? And Ananya, is that Ananya or somebody else from her account? When we arrange the sphere in the linear arrangement, it becomes the linear arrangement of the lattice points, that is the center of the spheres. Okay. And whatever, the only lattice parameter we require is the distance between the two lattice points, and we can simply arrange it thoroughly. So that's what we have as lattice. So this is the confusion that the sphere itself is a three-dimensional object, and how can it be arranged in one dimension? Actually, it is the arrangement of the center of mass of the spheres. If the center form a straight line, it is a linear arrangement. Okay. Each center of mass is considered a lattice point. सर कल नोट्स भेजना है सॉलिड स्टेट का? बेटा आज भी भेजना था, बिल्कुल भेजना है, रोज भेजना है सॉलिड स्टेट का नोट। तुम बना रहे हो ना? आई डोंट वांट यू टू मेक स्पेसिफिकली फॉर सेंडिंग, send the notes which you make in the class. Okay, I know Ananya, it's me only. If you are not Ananya, then also it is me only. Yes, Prerna, you have also sent it. Okay. Anybody who has not liked the session, go ahead and like it. We have 13 people watching the session and there are only 12 likes. That is bad. We need to have 13 likes at least. Each center of mass is considered a lattice point. So this is the linear arrangement. No problems with that? Now, once we have talked about the linear arrangement, each sphere is in contact with two of its neighbors. The number of nearest neighbor of a particle is called coordination number. So in a linear arrangement, the coordination number is 2. Anybody has any doubts? Somebody has already sent the notes, isn't it? For today's class. Who has sent it? I'll just check it out. Someone has sent the notes. Ananya has sent the notes of solid state. So we can have the look at the notes of sent by Ananya. You also can have a look at the notes sent by each other and see if you have missed any points. Okay? In this way, your notes will become even better. In one-dimensional arrangement, only one lattice parameter is required, and that is the distance between the two nearest lattice points. Now we talk about two-dimensional arrangements. And when we talk about the two-dimensional arrangement, it's simply like एनसीईआरटी में ना कुछ टेढ़ा मेढ़ा लिखा हुआ है. तो चलिए बात करते हैं टू डायमेंशनल अरेंजमेंट की, किस तरीके से वी कैन सी द टू डायमेंशनल अरेंजमेंट. So let's talk about the two-dimensional arrangement. Now, what kind of a structure can be repeated to give a two-dimensional arrangement? We have lot many two-dimensional structures. The simplest two-dimensional structure would be a triangle. Okay? The simplest two-dimensional structure will be a triangle. Now we can arrange the triangles in an arrangement. But the problem is if we arrange the triangles, then this part remains empty. Now you might say that we can make the upside down triangle, but rotation is not allowed. You cannot rotate it. Rotation is not allowed. So triangle, whether it be equilateral, isosceles, or scalene triangle, whatever it might be, we cannot use it as a repeating unit. So when we talk about the two-dimensional repeating unit which can be used, they can be what could be the two-dimensional repeating units. Possible 2D repeating units. Quite obviously, one repeating unit could be square. Okay. So let's talk about the possible 2D repeating units. One could be the square. That is possible. Okay. Then we could have a rectangle. Okay. Rectangle could also be a repeating unit. Then we could have a parallelogram. Fine. We can even have a rhombus. Okay. These could be the repeating units for two-dimensional arrangement. And one repeating unit which could be there for two-dimensional arrangement is what we term as a hexagon. When we talk about these lattice parameters, regular octagon, Mayuk, if we talk about regular octagon, will we not have gaps in it? If we talk about an octagon, okay, now this isn't regular octagon. If I copy it down, and I paste it, I place it here. Now this gap can't be filled. This gap can't be filled. We will not be able to fill it. Can you see that? Mayuk. So that is why a regular octagon cannot be used. Because here we are going to end up with a square as a gap. If you place it like here, let's say you take this arrangement, this part, place it like this. So there will always be a square gap in it. So a regular octagon cannot be used. We don't need to avoid the gaps. We cannot have the gaps. You do not listen to what I gave you the conditions for the repeating unit. A repeating unit must give the entire arrangement without rotation. And when we make the arrangement, there should not be any gaps. If there are gaps or we need to rotate, it's not an applicable repeating unit. And that is why we have only 4 kind of repeating units in the 2-dimensional arrangement. Other than that, we don't have any repeating units. Is it clear? Okay. When we talk about the square, here we again have the lattice parameter. Here we have the 2 dimensions A, and this angle is 90 degree. So we generally have the 2 sides as A and B. So we have A is equal to B, and the angle is 90 degrees. So we call this angle as maybe alpha, beta, or gamma. In case of rectangle, A is not equal to B, and the angle is 90 degree. In case of parallelogram, A is not equal to B, and the angle is not equal to 90 degree. In case of rhombus, A is equal to B and angle is not equal to 90 degree. Is this clear? So that is what we have as rhombus. But when we talk about the hexagon, hexagon is a peculiar case. Here A is equal to B and angle is equal to 60 degree, or you may call it 120 degree. So if you take this angle, it is going to be 120 degree. But if you take it as this way, this angle is 60 degree. So we can have 5 units which can be considered as repeating unit in the 2 dimensions. Okay, square, rectangle, rhombus, parallelogram, and a regular hexagon. Other than that, you cannot have anything which can be used as a repeating unit in 2 dimensions. अनन्या दिखा दूंगा बेटा 3D स्ट्रक्चर क्या वो पूरे के पूरे यूनिट्स दिखा दूंगा. इसी के लिए मैंने कल भी क्लास रखी है. वैसे कुछ स्ट्रक्चर तो मैं आपको दिखा ही सकता हूं. Like these structures. Can you see? This is sodium chloride arrangement. So we are going to see it more nicely a bit later. And this is what we have as a hexagonal arrangement. See? And this is what we have as a square arrangement. Can you see that? A square. A cubical arrangement, in fact, a cubical unit cell. So we are going to talk about this. Okay, so that's what we have as the arrangement. So now when tiles are placed to cover the floor, a repeated pattern is generated. And we can use only those two-dimensional structures which actually can be used as tiles on a floor. Is that okay? Is this clear? Now this is the NCRT. Now motif, when we call this particular as motif, motif is actually the molecule. This is the molecule. हाँ ये NCRT का line है. So not only we are doing it, somebody is asking me, sir, pop-off rule किया है. बेटा pop-off rule कोर्स में नहीं है. ठीक है? So this is what we have, but we are taking only the lattice point in this case. We are not talking about the entire arrangement. So this is what we have as a lattice point. This is what we have as arranged. And this is how we get the two-dimensional arrangement. Now these are the two types of arrangements. This is what we call as the square arrangement. This is the square. And this is what we have as the hexagonal. This is square two-dimensional arrangement. This is hexagonal two-dimensional arrangement. Is this clear? This is the repeating unit. Any kind of confusions here? So once we have the square arrangement, and then we have the hexagonal arrangement. This is the square arrangement, and this is the hexagonal arrangement. In case of square arrangement, as you can very well see, the coordination number is equal to 4. Each particle is attached by 4 other particles. Now here, if we talk about the hexagonal arrangement, it is coordination number is equal to 6. Each particle is surrounded by 6 other particles. So in two-dimensional square arrangement, the coordination number is 4. In two-dimensional hexagonal arrangement, the coordination number is 6. Clear? Now, if somebody asks you how many lattice points are required to make a square, the answer would be 4. Can anybody tell me how many lattice points are needed to make a hexagon? Give me the answer. Mike, we are going to talk about the gaps. Don't worry about it. How many lattice points are required to make a hexagon? Mayuk Sen Gupta, Priyanshu Ghosh, Tirthraj, Radhika, Ananya, Prerna. Six. Everybody has given me the answer six. The answer is seven. You forgot the central lattice point. There is seventh lattice point in the center as well. Yara silly, silly, beta silly, silly. You make a silly, silly mistake, but don't make it. Here we can easily have this kind of an arrangement. Here we have a circle. You arrange this particular. Hmm. You make this linear arrangement. Okay. Now this is the linear arrangement that you make. You place it like this. Now this becomes the square arrangement. This is the square arrangement, and as you can very well see here, the line goes. And there you can see this particular is attached to the particles. Okay, so here the coordination number is 4. But now we talk about the Again, we can talk about the spheres a little bit smaller. Now we copy it and see, I place it like this. Okay? Yeah. Now, if we consider this to be the arrangement A, this becomes the arrangement B, this again becomes A, this becomes B. So this is an AB-AB arrangement of the layers. Is this clear? And if I put the points here, you can very easily see the hexagon. Anywhere you can draw it, here is the hexagon. Is the hexagon representable, visible to all of you? So this is what we know as the hexagonal arrangement. Okay, this is the two-dimensional hexagonal arrangement. Now the arrangement in which all the lattice points making the basic shape lie on the corners is called a primitive arrangement. So a square arrangement is a primitive arrangement. Is that clear? Okay. Possible is parallelogram with sides length A and B. So we have got the hexagonal arrangement AB type of hexagonal arrangement. This is what we have here. So these are the five possible arrangements. Okay. This actually is hexagonal. Somehow they have messed it up. Now to talk about the three-dimensional arrangement. The real structures are three-dimensional structure and they can be obtained by stacking two-dimensional structure one above the other. Fine. The space lattice is a three-dimensional array or arrangement of points. Crystal structure obtained is by associating structural motifs with lattice points, each repeated basis of motif. Yeah, what is exactly it is. Now, when we talk about this three-dimensional arrangement, we have six lattice parameters. We have like six lattice parameters. What are the six lattice parameters? The six lattice parameters are three sides A, B, C and three angles alpha, beta, gamma. So we have the six lattice parameter to define a three-dimensional unit cell. Now here this is given in NCERT that alpha is between B and C, beta is between A and C, and gamma is between A and B. So that is what you need to, I don't know whether it is matter, remembering or not. I haven't seen anybody asking a question about alpha, beta, gamma, and ABC where the alpha, beta, and gamma happen to be present. So we don't need to bother about it. Okay, fine. Wow. This is all what happened here. So here we have, oh yeah, okay. So I believe we can see that this is beta, this is alpha, this is beta, this is gamma, this is C, this is A, and this is B. So that's what we have as the positioning of the various angles and the sides. Clear? Now these are the characteristics which we have already joined. We have already understood that what are the characteristics of the crystal lattice. Now this is what we have as the unit cell. Okay. Three-dimensional repeating unit is termed as the unit cell. कुछ गड़बड़ हो गई है कोई बात नहीं विल चेक इट आउट क्या गड़बड़ हुई है See, so we have something called the unit cell. So when we talk about the unit cell is the simplest 3D unit which, when repeated, gives 3D unit which give when repeated gives the entire lattice. So that is what we have as the thing called the unit cell. Is that clear? So that is what we have as the unit cell. So now we have to define the various types of unit cell depending on what could be the alpha, beta, gamma, and ABC. As such, they can be divided into two broad categories. We can define the primitive unit cell and the centered unit cell. When we talk about the primitive unit cell, it is quite obvious that the constituent particles are present only on the corner position of the unit cell. So these are what we call as the primitive unit cell. Okay. And then we have centered unit cell. Now, one or more constituent particles, that is the lattice points. When we talk about the constituent particles, we are actually talking about the lattice points. They are present at the positions other than the corners. In addition to that, to those at the corners. So it is not that key. The particles are not present at the corners. They are present at the corners, but in addition to being present at the corner, they are present at the centers also. And where centers could be present? They could be present at the body center, okay, where the particle is present in the body center besides the one at the corner, or it could be face center. That is, they are present at the center of all the faces. And then there is something called the end centered. Now, end center is a face centered where only two opposing faces are occupied. So that is what we have as the face center. Clear? So that is only two opposite faces are occupied, but others are not occupied. So that is what we call as the end-centered unit cell. Okay. Now there are seven basic crystal systems. By getting alpha, beta, gamma, A, B, C, the seven basic crystal systems can be formed. Now, these seven basic systems can be realized in 28 ways. But out of those 28, 14 are impossible arrangements. So there are only 14 possible arrangements in which the seven basic crystal systems can be realized. Okay. Simple is the primitive arrangement, body, face, and end centered. That are the centered arrangements. Now here these are called the Bravais lattices. There are 14 Bravais lattices distributed in seven crystal systems. So there are seven Bravais lattice distributed in, there are 14 Bravais lattice distributed in seven crystal systems. Okay. So these are seven crystal systems: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. So these are seven crystal systems. Okay. And these seven crystal systems, these have the different Bravais lattices. Like when we talk about the cubic has primitive body centered and face centered. Tetragonal. Now, these arrangements again are classified according to the ABC and alpha, beta, gamma. This is to be learned. This part you have to learn. Okay, this part you have to learn. So this table as such is to be learned. Okay. The examples are not that much important because examples are not normally asked, but these are the things which you have to learn. एग्जाम्पल ज्यादा नहीं पूछे जाते बट ये टेबल पूछा जाता है. सीधा सीधा आपको ये दे दिया जाएगा व्हाट इज ए बी सी एंड अल्फा बीटा गामा आर दीज which kind of arrangement it is, or if this is a orthorhombic arrangement, what is the ABC and alpha beta gamma. Okay, now these are the Bravais lattices. This one is cubic, this one is tetragonal, this one is orthorhombic. So here we have 3, here we have 2, here we have 4. 3 plus 2 5, 5 plus 4 9, and here we have the angles, the hexagonal lattice. Hexagonal again is 2. Okay. Possible variation is whether they can be centered units or not, whether they can be simple only or they can be centered also. Okay. Now we are going to talk about the crystal systems, and we are going to talk about the arrangements that we can obtain from the two-dimensional arrangements. That is, we have the square arrangement, we have the hexagonal arrangement. What are the possible arrangements that we can get? Is it clear? Now we can talk about something like square plate packed arrangements. Square packed arrangement, we have the square arrangement and we place the square arrangement on top of it. So if it place square on the top of the square, we get this arrangement. See, the square arrangement has been placed on the square arrangement and we get a cubical arrangement. So this is the arrangement of square on square, the cubical arrangement. Okay. In this arrangement, the spheres of both the layers are perfectly aligned. One sphere is on the top of the other sphere, and that is what we have as the arrangement. Now we can keep on placing the arrangement and we are going to get AAA arrangement, AA type arrangement. All the layers have the same arrangement. This is a simple cubic lattice and its unit cell is the primitive cubic unit cell. This is a primitive cubic unit cell. Is this clear? Yes, crystal is absolutely clear. So this is the cubical arrangement. Anybody has to ask it? Anyone has to ask anything here? Okay, now we get along with how to define the cubical arrangement. Let's get a square. Okay. Here is a square. Here is the cube. Now this is a simple cube. Now we are going to talk about the different properties of a simple cubic arrangement. Let's talk about the properties of a simple cubic arrangement. Okay. Clear? Now, in a simple cubic arrangement, the particle is placed at this point, here, 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 and here. Now let us see how many particles a given particle is shared with. The particle is at the corner. So the contribution, as we have discussed earlier, is equal to 1 by 8. The corner, the contribution is 1 by 8. Okay. There are 8 corners. So total contribution becomes equal to 1 by 8 multiplied by 8. So that becomes equal to 1. So the total contribution in a cubic unit cell is 1. Can anybody tell me the coordination of each particle in a cubic unit cell? As you can very well see here, we have one, two, three, four, five, and six. So the coordination number is not eight. Coordination number is actually six. Contribution is one. Coordination is six. Now, when we talk about this edge length, let's talk about the distance between the two. This particle, this is going to be one sphere. This is going to be another sphere. Now these spheres, they are going to touch each other, and this is the distance between them. Now this distance is r, this distance is r, so the net distance turns out to be 2r. So this distance is going to be 2r, that is equal to the edge length A. Is it clear? For a simple cubic arrangement, the edge length is twice the radius of the sphere making the arrangement. Fine? Okay. Now we have talked about the coordination, we have talked about the contribution, and we have talked about the edge length A is equal to twice of R. Once we have talked about the edge length A, we can even talk about the volume of the cube. Now volume is A cube because it's a cube, so it is going to be 2R whole cube. Okay, that will turn out to be 8R cube. So the volume of the simple cubic unit cell is 8R cube, where R is the radius of the sphere making the arrangement. Okay. Now, let us talk about the mass of cube or unit cell. Now, mass of the unit cell will be equal to molar mass divided by the Avogadro's number multiplied by the contribution Z. The contribution Z is equal to 1. So, it is going to become M divided by Na multiplied by Z. So, M is the molar mass. Okay, Blue, is it clear? Now, we have talked about the molar mass, we have got the volume, so we can even get something like density. So we can talk about density. Density is equal to mass by volume. Now, mass is equal to Z multiplied by capital M divided by the Avogadro's number. Volume is equal to A cube. Now, that becomes Z. Z is 1. Simple cubic arrangement, Z is 1. 1 into M divided by Na into 8R cube. So this is the density of a simple cubic arrangement. Clear? And now we have a very important thing that is called the packing efficiency. Packing efficiency. Packing efficiency is eta. Now that is equal to the volume occupied by the particles in it divided by the total volume of the unit cell. So that is actually equal to Z into 4 by 3 pi r cube divided by the volume of unit cell. Now this eta for a simple cubic arrangement is equal to 1 into 4 by 3 pi r cube divided by 8r cube. Okay, could you give me the answer in terms of pi and the fraction itself? Answer. So we have 4, it goes to, here is r cube gone, and we get is as pi by 6. This is approximately 0.52. So we can say the efficiency, the packing efficiency of a simple cubic arrangement is 52%. So that was a simple cubic arrangement. Now let's get along with another thing which we call as a body centered arrangement. Okay, we get a body centered arrangement. What is the meaning of the body centered arrangement? Body centered arrangement would mean that we have a cube. Okay, this is the cube, and apart from placing the particles at the corner, apart from placing the particles at the corner, we place the particle in the center as well. Now this is the body center. So this is a body centered cube. Fine. Priyanshu, you can learn the packing efficiency values, and I have also derived it, so that should not be a problem. Is this clear? So this is what we have as the body centered arrangement. Now in this case of body centered arrangement, again we talk about the same things. First of all, we talk about the contribution. Let's say we talk about the contribution. This is a contribution of 1 by 8. This is a contribution of 1. So it is going to be equal to 8 into 1 by 8 plus 1. So this comes out to be 2. So this is what we have as contribution. Now let's talk about the coordination. Now when you can see this part, this particular, it is attached to this 1, 2, 3, 4, 5, 6, 7, 8. So the coordination number is 8. Is it clear? So the coordination in a body-centered cubic arrangement is 8. Now let's talk about the edge length. Now one thing you need to understand that here the two particles do not touch each other. This particle in the center of the cube has pushed them apart, so they do not touch each other. But these particles are the ones which touch each other. So these particles, they touch each other. Clear? Now, the body diagonal of a cube is equal to under root 3 of the edge length. Yeah. Now, how long is this body diagonal? Now, this part is radius. This part is radius and this part is radius. And this part is radius. So, body diagonal is actually equal to 4r. Anybody has any doubts with that? Now, this is the confusing part most of the students have a doubt in. So, anybody has any kind of doubts here? Is that clear? So, root 3a is equal to 4r. So, a is equal to 4 by root 3r. Okay. So, when we talk about the volume, volume is going to be a cube that is equal to 4 by under root 3r whole cube. So, we have got the volume. Let's say we talk about the mass. Mass is equal to Z into m divided by Na. Now that is equal to 2 into molar mass m divided by Avogadro's number. Okay. So we have the density. That is, you can write it as D or you can write it as rho is equal to 2 multiplied by m divided by NA into 4 by under root 3 R whole cube. So this is what we have as the density of a body-centered cubic arrangement. Now let's talk about the packing efficiency. Radhika, could you give it in terms of pi and the fraction? When I talk about the packing efficiency eta for our body-centered cubic arrangement is going to be 2 into 4 by 3 pi r cube divided by 4 by under root 3 r whole cube. Could you give me the value of it? This will turn to be 2 into 4 pi r cube divided by 4 into 4 into 4. Here we are going to get into 3 into under root 3. Here we are going to get 3. And here we have r cube. So let's find out what exactly is the value. R cube get cancelled with r cube. 3 goes with 3. 4 goes with 4. And this 2 goes with 4. 2's are. So here it comes out to be equal to root 3 pi by 8. Now that when turned into the decimals, it comes out to be something like 0.68. So eta for a body-centered cubic arrangement is similar to 68%. नीलिमा, फोन का चार्ज खत्म हो गया। कोई बात नहीं बेटा, अभी डेटा भी खत्म होगा। Now we are going to get along with another one, and we talk about the face-centered cubic unit cell. हाँ ऋतिक प्रसाद, maximum students are from West Bengal state. So we have the face-centered cubic unit cell. Now let's see how the face-centered cubic unit cell goes on. So here we have the arrangement. This is the solid the arrangement. And let's make it a little bigger. Okay. Or rather, I should say, इसको ऐसे ही रहने दो. And let's put one more. Okay. Let us divide this particular unit into the different fractions, different parts. Okay. And then I have now let's place the atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13, and 14. So we need 14 lattice points to make one face-centered cubic unit cell. Okay, let's place it here. Okay, now very first thing. Can anybody tell me the coordination number of this particular point? Let's talk about the coordination number of this number point. In case of face-centered cubic arrangement, the coordination number is the most difficult part. हाँ जी, कितना है coordination number? Yes, the coordination number is 12. Does anybody have any problem? The coordination number here would be like this. This is going to be joint here. 1, 2. These are all equidistant from it. 4. Okay, this is 4. 5, 6, 7, 8. Okay, this one is 9, 10, 11, 12. Okay, so the coordination number here is 12. Now let's talk about the contribution. There are contribution Z. There are 8 corners, each having a contribution of 1 by 8. And then there are 6 faces, each having a contribution of 1 by 2. So the total contribution turns out to be 1 plus 3 equal to 4. So here the contribution is 4. Any doubts? So let's talk about the density directly. No, density. We need to talk about the edge length, A. Now here again, these parts do not touch, but this part, the particles on the face center, they touch each other. Now this is going to be R, this is going to be R, R, and R. So the face diagonal is equal to 4R. Face diagonal is equal to 4R, and that is equal to root 2A. The diagonal of a square is root 2A. Clear? So A will be equal to 4R by root 2, and this is equal to 2 root 2R. Is that clear? Now let's talk about the density. Density would be equal to 4m divided by Na into a cube, and that would be equal to 4m divided by Na into 2 root 2r whole cube. Is this clear? Now that's what we have talked about. Okay, now let's talk about the packing efficiency. Packing efficiency eta would be equal to Z into 4 by 3 pi r cube divided by V. Now that's going to be equal to 4 into 4 by 3 pi r cube divided by 2 root 2 r whole cube. Okay, let's solve it. It becomes 4 into 4 into pi r cube divided by 4 divided by 3 into 2 cube is 8 into root 2 square is 4 into root 2, okay, r cube. Okay, let's cancel it. How do we get it? So here we get 4 goes with 4, 4 goes with 8, here it is 2. Okay, r cube goes with r cube. Here it should be 2 only. क्या कर रहा हूं मैं? This one is not 4, this one is only 2. Okay, so this 2 also goes off. And what we are left over with is pi divided by 3 root 2. Now that can be written as root 2 pi by 6. Now root 2 pi by 6, if I solve it, that is approximately 0.74. So eta of a face-centered cubic arrangement is simply somehow like 74%. Anyone has any confusions here? Any problems? So this is what we have as the various things. This is what we already done. So this is for a simple cubic arrangement. Can you see that? आज स्पेशल क्लास नहीं है. This is what we have as density. Can you give me the answer to this question? नहीं है बेटा अक्षय, आज मैंने नहीं रखा. आज मैंने स्पेशल क्लास नहीं रखी है. आंसर. Answer. Priyanshu Ghosh, it's okay, but it's less than 1000, but what's the number? How many? Less than 1000 is okay, but what's the number? हाँ बेटा कल भी वाईटी सेशन है दो सेशन ऑलरेडी लग चुके हैं वन इज फॉर द सॉलिड स्टेट वन इज फॉर केमिकल काइनेटिक्स आंसर simple as that understand that this is a simple cubic arrangement. The boxes are going to be arranged in a simple cubic arrangement. And when the boxes are arranged in a simple cubic arrangement, the efficiency is pi by 6. That is approximately 52%. So it is going to be actually 52 by 100 into 1000 decimeter cube. So that will turn out to be 520 boxes. It's a single line answer. It's not a multiple line answer, but you need to see that this is a simple cubic arrangement. And that is how the knowledge of solid state is used in the real life. Clear? So this is the body-centered cubic arrangement. We have already done that. As you can very well see, the body-centered cubic arrangement, the particles placed on the corner, body, and the opposite corner, that is body diagonals, they touch each other. Anybody who has not liked the session, go ahead and like it. So this is what we have as the packing efficiency. This is what we have as the body-centered arrangement. Now let's talk about the hexagonal closest packing. Okay. I believe we can have a 3-minute break. Okay, we have a 3-minute break. Start at 5:55. ओके पानी वगैरह पी के आ जाओ फटाफट Should we begin? स्वाति मैम का सेशन है, कौन सा सेशन है? स्पेशल क्लास? So let's talk about the hexagonal arrangement. Okay. Now, this is a hexagonal arrangement. As you can very well see, this is the hexagonal arrangement. There are two ways we can place the hexagonal arrangement over the other arrangement. Now let us see how we can arrange the hexagonal layers. I believe we have to wait till tomorrow so we can see that. स्वाति मैम का सेशन है 6 बजे से. चलो एक काम करते हैं. Let's end the session today and we'll start with it tomorrow in the morning, 10 o'clock. Is that clear? So unlock our biggest offer, get 25% off on all Plus and Store subscription. Iconic Mega Sale Week is here. AV Live code. 2 p.m. from Monday to Friday. We have Botany at 2 p.m., Zoology at 3 p.m., and Chemistry at 4 p.m. Telegram channel for YouTube classes PDF, t.me/Neet Elixir. Neet UG subscription, go ahead and join it. And this is our goal. Join with unacademy.com/Anoop Vashishtha and make the notes and send it. So subscribe to the Neet Elixir by Unacademy for the best live classes. Like, share, and subscribe. Bye-bye. We are going to meet in the next class tomorrow morning at 10 a.m. Bye-bye. Take care.